Okay, we will talk about equivalent circuits in this video. So in the past, we have seen equivalent resistances. For example, we have seen equivalent resistances for series and parallel combinations. And equivalent circuit is just a general term for basically any element, not just resistors. So 1 by R equivalent equals 1 by R1 plus 1 by R2. Yeah, so we have seen this before, series and parallel combinations of resistors. Now we will talk about we'll talk about them in general. So you can have, for example, voltage sources in series, or maybe you have current sources in parallel, or maybe you have a voltage source in series with a resistance or something like that. You can have a lot of combinations, right? So we will talk about them here. So what makes two circuits equivalent? So if you have a large circuit, say something like this, and there you find a smaller part of the circuit, say, let's call it sub-circuit A. I'm calling it sub-circuit because it's a smaller part of the whole large circuit. And you change everything inside the box. You change the circuit A with something. So maybe you have another circuit you replace it with, say that's circuit B. But turns out that everything outside the box is just as same as before. So the node voltages here, so V1, V2, node voltages there, and the currents going in and currents going out are exactly same as it was before with circuit A. So the node voltages were exactly the same here, here as well. So everything else outside the box is exactly same after you have changed the circuit. So if such so if you find such a circuit for that circuit sets A and B, that you can swap them out but still nothing changes, then we call them equivalent, because that's what it means to be equivalent, right? You can swap circuit A with swaps and swap circuit A with circuit B, and nothing actually changes outside the box. For example, maybe you have this circuit and you see that there are two resistances in series, one with 5 ohm resistance and another with 3 ohm resistance. And if you swap that out with, say, one resistor that has a value of 8 ohm, you will see that nothing outside the box actually changes. And that's why we call them equivalent, right? So how can you find the equivalent circuits, or what's the criteria that makes them equivalent? Well, if you can find two circuits that has the same exact equation just outside the box, and just outside the box you have only two things, the terminals. So these terminals, if you find that the relationship between V1, V2 and the terminal voltages and terminal currents are exactly same in both circuits, then they are equivalent. And we can actually show that. So let's do that. So what's the relation between the terminal voltages V1, V2 and the terminal current I? So we can apply Ohm's law here on the left. Basically you have one current I going through the whole resistor. So you can just write V2 minus V1 equals 8I following the passive sign convention. So this is the relationship between the terminal voltages and the terminal current. Okay? And what about the circuit on the right? Well, we have one more node here, so let's call it V3, and we still have one current going through them, so we have current I and also current I here. Remember, series connection has only one current going through all of them. That's what it means for them to be in series. So here for the 3 ohm resistor we can write V2 minus V3 equals 3I, and for the 5 ohm resistor we can write V3 minus V1 equals 5I. And if you add them up, you can cancel V3. You will have an equation V2 minus V1 equals 5 plus 3, 8I. So this circuit on the right also has the exact same equation as on the left. That's what I was talking about. So when you find two circuits, circuit A and circuit B, with exact same relation or equation between terminal voltage and currents, we say they are equivalent. So circuit A and circuit B are equivalent, and in any circuit you can find that combination, you can swap them out with its equivalent circuit. That's what it means to be equivalent. So let's try it out with parallel connection as well. So let's try it with 3 resistors this time. Say we have a 4 ohm resistor, we have a 6 ohm resistor, and we have a 12 ohm resistor. So I want to replace this 3 resistors with something, and so everything outside this box will be same as before. So the terminal V1, V2 and the current going through them will be the same. So one thing to notice here, that the current I will actually split up into 3 branches and 3 currents. So let's call them I1, I2 and I3. And if you apply KCL there, you can easily see that I should be equal to I1 plus I2 and plus I3. Of course, because I current is splitting up into 3 parts. And those parts are going to meet up again on this side. So they will add up again and you'll have the same current going out. So you have the same current I going out. Okay. So now we want to see what's the relationship between V1, V2 and the current I. So let's write equation Ohm's law for each of these resistors. So first of all, we have V2 minus V1 equals 4I. By the way, we have only 2 nodes here, node 1 and node 2. So this is one huge node and this is another huge node. So we have V2 minus V1 equals 4I1, sorry, because the current going through the 4 ohm resistor is I1. Let's write it like this. I1 equals 1 by 4 V2 minus V1. And you can similarly write I2 equals 1 by 6 V2 minus V1 for the 6 ohm resistor. And for the 12 ohm resistor, you can write I3 equals 1 by 12 V2 minus V1. And if you add them up, you will have I1 plus I2 plus I3 on the left side. And on the right side you will have 1 by 4 V2 minus V1 plus 1 by 6 V2 minus V1 plus 1 by 12 V2 minus V1. Okay, so now as you can see here, I1 plus I2 plus I3 is just I, and if you take V2 minus V1 as the common term, you will have 1 by 4 plus 1 by 6 plus 1 by 12. And if you actually calculate this, you will see that it's equal to V2 minus V1 times 1 by 2. So this is the equation between the terminal voltages and current. Okay? And if you find another circuit with the same equation for the terminal voltage currents, then they are equivalent. And I don't know if you can tell, if you take a 2 ohm resistor, it will give you that same equation, right? Because if you look outside this box, you have V1, V2, and maybe a current going through them is I. So you write V2 minus V1 equals 2I, or in other words, I equals 1 by 2 V2 minus V1. So this is the exact same equation as before. So these three resistors in parallel are equivalent to this just one resistor with 2 ohm resistance. Okay, so if you find the terminal voltages to be same, then the terminal voltage current relation to be same, then they are equivalent. So these things you have seen before. Now can we extend this to newer ideas? So first, the easiest question will be what's 0 volt voltage source is equivalent to? What 0 volt voltage source is equivalent to? So if you look outside this box, you will see there's two nodes, V1, V2, and of course there is a current, but that doesn't matter much because the equation for this will be V1 minus V2 equals 0, and you will have V1 equals V2. So the voltages are same on both terminals, and this is actually equivalent to just a piece of wire, because if you have a piece of wire, the terminal voltages and any voltage on the wire basically is exactly same. So V1 must be equal to V2. So here we have the same equation for two circuits and they are equivalent. So if you find a 0 volt voltage source somewhere, you can replace it with just a piece of wire, or as we sometimes like to call it, a short circuit connection. So we call a piece of wire sometimes a short circuit connection, just a technical term. Okay, so 0 volt voltage source is equivalent to a short circuit connection. Okay, there's one more similar to this. So what would a 0 ampere current source be equivalent to? What's this equivalent to? Well, again, we have V1, V2 here with a current I, and the voltages this time doesn't matter. The equation will be I equals 0. And this is actually equivalent to just a broken piece of wire. So there is no connection between them, right? Because if we don't have a connection, if you remember, say we have air in between them or something like that. So we have an insulator in between them. So current cannot pass through them. So the current here is 0. So there is no current. So if you use an insulator, I mean, you don't have to. Just if you break a wire, there's air everywhere, and air is an insulator. So the current here is also 0. So the equation on both of these both of these circuits are same. So a 0 ampere current source is just equivalent to a broken piece of wire, or as we like to call it, open circuit connection. Okay, so the circuit is open and the current cannot pass through them. So the circuit is open and the current electrons cannot pass through them. Okay, so a 0 ampere current source is equivalent to open source connection. This is what we call open circuit connection. And we call a piece of wire, this is what we call a short circuit current, because current can pass through them without any resistance. Okay, a short circuit connection. Okay, so they are equivalent as well. What more can we do? Well, we have seen that voltage sources. So we can have voltage sources in series connection. Let's say we have two voltage sources, 5 volt and 3 volt in series connection, and say we want to replace this with its equivalent circuit. So again, we have two nodes on the outside, two terminal nodes, and maybe one current is going through them, but that doesn't matter because here we are dealing with voltage sources, so current will not be in any equation either way. So here, first of all, we have a new another node here. Let's call it V3. So for the 5 volt voltage source, we have V1 minus V3 equals 5, and for the 3 volt voltage source, we have V3 minus V2 equals 3 volt. So again, if we add them up, the V3s cancel out, and we have V1 minus V2 equals 5 plus 3, 8. So if we find another circuit that has exactly this equation, then they are equivalent. And you can probably say which circuit this is. So if you have just a 8 volt voltage source, outside the box you will have V1 and V2, and the equation for the terminal voltages will be V1 minus V2 equals 8. So the equations are exactly same, so they are equivalent. So just like resistances, voltage sources in series just simply add up. Okay, but one thing you have to be careful about though, because voltage sources can face different directions. For example, if I had the other circuit, so let's say I have another circuit that has the 5 volt flipped. So this is 3 volt just like before, and this is 5 volt just like before, but the directions are different. So this is how the plus minus here looks, and this is how it was before. So the voltage source is now flipped. So what will be the equivalent circuit for this? So let's see, let's do the exact same thing here, V1, V2, and let's call the middle node V3. So we have V3 minus V1 equals to 5 this time, not the other way around. Always remember positive terminal minus negative terminal. Then we have V3 minus V2 equals 3. And as you can see, we cannot actually cancel them out unless we multiply them with -1. So let's multiply this one with -1. So this becomes plus and this becomes minus. And now if we add them up, we cancel out the V3s, and we have V2 minus V1 equals 5 plus minus 3, which is 2. So this will actually be equivalent to just a 2 volt voltage source like this, right? And this will be V1 and V2, because here you will have the exact same equation, V2 minus V1 equals 2. So we have same equation, that's why these two circuits are equivalent. So you have to be careful about the polarities. You can actually think of them like this. You can think of the 3 volt voltage source like this. The positive negative terminals are flipped and the value is flipped as well. So double negative, they cancels out. And if you add 5 plus -3, you get just a 2 volts. So just like before, you can add them up if they're facing the same direction. Okay. All right. That's about voltage sources in series. Now, what about voltage sources in parallel connections? So let's say you have 5 volt here and 3 volts here in parallel connection. What will be the equivalent circuit for this? Well, this is a bit of trick question because this is actually illegal. So you cannot have 2 voltage sources in parallel connection. That is because if you look at the 5 volt voltage source, you can say that V1 minus V2 equals 5. And if you look at the 3 volt voltage source, you can say V1 minus V2 must be 3. So which one is it? Is V1 minus V2 equals to 5 or is it equals to 3? So there is a conflict here. So we can never connect 2 voltage sources in parallel. If you do, that will lead to mathematical errors of some sort. Okay, so this is actually an illegal move. So in circuits you can never have voltage sources in parallel connection. This is illegal. So you can never have voltage sources in parallel connections. Okay, so now what about current sources? Well, let's say you have 2 current sources in series connection, so 5 amperes and 3 amperes. What's the equivalent circuit for this? Well, this is also an illegal move because there is only one current going through this branch, right? So the current has no other way to go. So I is equals to either 5 or I is equals to 3. They cannot be both at the same time. So current sources in series also creates conflicts. So current sources are also not allowed. Current sources are also not allowed in series combination. Okay, so basically current sources are exact opposite of voltage sources. Okay, so you cannot have them. You cannot have current sources in series connection and voltage sources in parallel connection. But you can have current sources in parallel connections. Okay, so this is okay. So 5 ampere and 3 ampere. This is not okay, but current sources in parallel connection is perfectly okay. All right. So if I ask you what's the equivalent circuit for this, well, again you have V1, V2 and current I outside, and that current will pass through them, and you can actually see that the current, if you apply a KCL here, you can easily see that I is equals to 3 plus 5, so I is equals to just 8. So instead of this, if you just use one 8 ampere current source, you will have the exact same equation and exact same voltages outside, so they are equivalent. So voltage sources in series, they add up. Current sources in parallel, they also add up. But voltage sources in parallel or current sources in series are not allowed. So keep them in mind, okay? So this is all I wanted to talk about for equivalent circuits. There is one more equivalent circuit I want to talk about, the one I drew on the first section of this video. So I said a voltage source and resistance can be in series. What's the equivalent circuit for this? So this combination actually comes up a lot in our circuits. So we will have a separate video on this, and it also has a nice name for it called source transformation. So I will have a separate video for that. Okay.